Hello everyone. In this video I want to show you an example of how to solve an equilibrium problem. So let's start off with our problem. If we have 0.5 molar HF and we're reacting with 0.3 molar of our fluoride anion, what will be the equilibrium concentration values? Okay, so our equation first is HF reacting with water to produce our fluoride anion and hydronium ion. So we already can start out with some of our initial values. So we have 0.5 over here. Our water, of course, it doesn't matter because as a pure liquid, it's not going to participate in our equilibrium expression. Our fluoride anions are 0.3 molar. And our hydronium ion is 0 molar. So we don't have any of our hydronium ion initially. The first step that we have to do is calculate our reaction quotient to determine which direction our reaction is going to proceed in. So our reaction quotient is equal to the ratio of our products over our reactants, each raised to their stoichiometric coefficients. So we have fluoride ion H3O plus over our HF. So this becomes then 0 times 0.3 over 0.5, which of course equals 0 since we don't have any of our initial hydronium ion. Since our Q value is equal to 0, our K value for this reaction, which of course would be given in the problem, is K equals to 6.76 times 10 to the negative fourth. Q is less than K, so the reaction proceeds forward. So what that tells us is that we're going to be producing more of our products. So we're going to consume our reactants, HF, and we're going to produce more of our fluoride ions as well as more of our hydronium ions. So this is our change as we approach equilibrium. We then have our equilibrium values will be 0.5 minus X. We consume some of our initial HF reactant. We're going to produce an additional X amount of our fluoride ions, and we'll also, at equilibrium, have X amount of our hydronium ions as we react to produce that equilibrium. So this allows us to set up our equilibrium expression. K equals 6.76 times 10 to the negative fourth equals our products. So that would be our 0.3 plus X multiplied by our X value divided by our reactants, our 0.5 minus X. We can then multiply both sides by 0.5 minus X. So this will eliminate our 0.5 minus X value, and we just get 0.3 plus X times X equals 3.38 times 10 to the negative fourth minus 6.76 times 10 to the negative fourth X. Now we can multiply X by each of our individual terms here to simplify on this side. So we have 0.3x plus x squared. And now we can add our components from the right side to the left side in order to get our equation that we'll use to solve the quadratic formula. So we add 6.76 times 10 to the negative fourth x. So our new equation, after we rearrange, so 0.3 plus the 6.76 times 10 to the negative fourth, so 0.300, just round it up to 7x. We have x squared here, plus the 0.3007x from our two x components, and then we're subtracting our 3.38 times 10 to the negative fourth. And that's equal to 0. So now this gives us our a, b, and c values for our quadratic equation. A would be equal to 1 here. B is equal to our 0.3007. And c is equal to our negative 3.38 times 10 to the negative fourth. Since our b value is positive, so our quadratic formula is x equals minus b plus minus square root of b squared minus 4ac divided by 2a. There's our quadratic formula. We know that negative b is going to be a negative term, so we're going to want to use the plus side variant so that our final x value will be positive. Right? We always want x to be positive. Okay, so now we can substitute our values into the quadratic equation. Let's go ahead and get this out of the way. So we have negative 0.3007 plus the square root of 0.3007 squared minus 4 times 1 times negative 3.38 times 10 to the negative fourth. On the bottom we have 2 times 1, or 2. This would simplify to negative 0.3007 plus, this comes out to, this would be 0.0904. This comes out to 0.3034. Or no, 0.001352. And so when we combine these terms and take our square root, we get 0.3034. Divided by 2. We can then add these together, divide by 2, and we should get approximately 1.1. And this would be in millimolar. So it comes out to 0.00112 molar. So this is our value for x. It's a positive number as we expect. So now we can use that value of x to solve for our equilibrium concentration values. If you remember from our ICE table, our concentration of HF was equal to 0.5 minus x. So 0.5 minus 0.00112 molar would be 0.499 molar. Our fluoride concentration is equal to 0.3 plus x, again from our ICE table. This will come out to 0.301 molar. And then finally our hydronium ion concentration is just equal to the value of x, or 0.00112 molar. So here we have our final equilibrium values. As you might notice, our reaction was very small, right? We didn't have a large change, and that's again because our equilibrium constant is relatively small. So with a small equilibrium constant, we won't react very far in the direction towards our products. So we produce only a small amount of those final products in our reaction. Our reactant then is relatively unchanged, and our product only increases by a small amount.